This is the final video where we'll be learning about the basic examples of spinors in physics. In the last couple videos, we've learned how both light wave polarizations and quantum spin states can be described mathematically by pairs of complex numbers called spinors that rotate on a sphere with SU2 matrices. In this video, we'll learn how to visualize spinors as flagpoles on a sphere, and learn how spinors are points on the complex projective line. To begin, let's review some of the basic facts about Jones vectors and quantum spin state vectors. A diagonally polarized wave is made up of equal amounts of horizontally and vertically polarized waves. However, if we phase shift the horizontally and vertically polarized waves by the same amount, all this does is shift the entire wave along the axis of travel. The wave is still diagonally polarized, so the polarization is unchanged. So we know that multiplying a Jones vector by an overall phase does not change the polarization. Here's something else to consider. If we take a diagonally polarized Jones vector and multiply it by 2, all this does is double the amplitude of the wave. But the wave is still diagonally polarized, so the polarization is unchanged. So we've learned that multiplying a Jones vector by an overall scaling factor does not change the polarization. So polarizations are unchanged when we multiply a wave by any overall phase factor or any overall scaling factor. And of course, a scaling factor and a phase together can be used to describe any complex number. This is just an alternative way of writing a complex number x plus iy. So polarizations are unchanged when we multiply Jones vectors by a complex number. Now let's look at quantum spin states in the Stern-Gerlach experiment. We know that when we take a particle with a given spin state and apply an inhomogeneous magnetic field, the particle will exit the magnet as a quantum superposition of two outcome states that are split in the up and down directions. I was a bit imprecise about this in my last video, but the state doesn't fully collapse into the spin up or spin down state until a measurement is performed at a detector. The probabilities for collapsing into a given state are given by the squared magnitudes of the inner product of the states before and after the collapse. This is called Born's rule. If we multiply our initial state vector by an overall phase and then look at the results of Born's rule, the complex phase comes out and has a magnitude of 1, leaving the resulting probabilities unchanged. What this means is that any two state vectors that are related by a complex phase represent the same quantum state, so quantum states are unchanged by overall phase factors. Now let's consider multiplying a quantum state vector by the number 2. In many introductory quantum mechanics classes, your professor might tell you that this is not allowed, because this can give us probabilities larger than 1 when we use Born's rule. Professors might tell you that it's required that all quantum state vectors must have a length of 1 to ensure that the probabilities of all possible collapsed states add up to 1. However, we can actually allow quantum state vectors to have lengths larger or smaller than 1, if we make an appropriate change to Born's rule. This new version of Born's rule contains a division by the squared vector lengths, which normalizes both vectors to have a length of 1. With the new Born's rule, we can feel free to change the lengths of our state vectors as we like, as long as they are non-zero, because the new Born's rule will normalize them to 1 for us. So if we multiply the first state vector by 2, we get a factor of 2 squared in the denominator, which cancels with 2 squared in the numerator, leaving the probability result from Born's rule unchanged. So it's only the angle between states that matters, not the lengths of the state vectors. So with the new Born's rule, multiplying a quantum state vector by an overall phase, by an overall scaling factor, or both leaves the state unchanged. So both Jones vectors for light waves and quantum state vectors in the Stern-Gerlach experiment can be written as a pair of complex numbers. And both of these can be multiplied by an overall scaling factor and an overall complex phase without changing the state they represent. We call these pairs of complex numbers that don't care about overall complex multiplication spinors. So we can write spinors as a pair of complex numbers, alpha and beta. These two complex numbers are made up of 4 real numbers, 2 scaling factors, and 2 phases. This might make you think that spinors require 4 real numbers to be specified. But since we are free to multiply a spinor by any complex number without changing it, we can always multiply by 1 over alpha, causing the top component to be 1 and making the bottom component the ratio beta over alpha. So really, there's only one complex number that's required to specify a spinor, since it is only the ratio of beta over alpha that actually matters, and this is a single complex number with 2 real parameters. This is why we're able to visualize spinors as arrows on a sphere. Only 2 real parameters are needed to specify them, the longitude and the latitude. The remaining 2 parameters, the overall phase and overall scaling, are ignored. However, we can still visualize the overall phase and overall scaling if we like, using a flagpole visualization. Instead of drawing a spinor as an arrow on this sphere, we can instead draw it as a flag on a flagpole. The orientation of this flag on the flagpole represents the overall phase factor that we're ignoring. We can also change the length of the flagpole to represent the overall scale factor that we're ignoring, so that it can be less than or greater than 1, as long as it's not 0. Note that a specific spinor is only identified with the point where the flagpole meets the sphere, so changing the angle of the flag and changing the flagpole's length do not change which spinor we're talking about. We can see these factors mathematically if we write out our spinor as a combination of 2 basis spinors, each with complex number coefficients. If we multiply and divide the second term by e to the I phi 1, we can factor out e to the I phi 1 from both terms and bring it out in front. If we take the spinor's magnitude to be m, we can multiply and divide both terms by m, then bring a factor m out in front. The ratios a1 over m and a2 over m can be visualized on a triangle like this. a1 over m is just the cosine of this angle, and a2 over m is just the sine of this angle. You'll notice that I've chosen to write this angle as theta over 2. This is because, in the original space, the 2 basis spinors are 90 degrees apart. But on this sphere, where we ignore overall signs, they are 180 degrees apart. So we need to take this angle on the sphere and divide it by 2 to get the correct angle between the basis spinors in the original space. So we can rewrite a1 over m as a cosine and rewrite a2 over m as a sine. I'll also rewrite phi 1 as omega and rewrite the phase difference phi 2 minus phi 1 as just phi. So we've rewritten our 2-component spinor like this, and it has 4 real parameters: m, omega, theta, and phi. The theta and phi parameters determine where the spinor points on the sphere. Omega is the overall phase, and determines the angle of the flag on the flagpole. And m, which is the overall magnitude, determines the length of the flagpole. The omega and m parameters can be ignored, since overall phases and overall scaling factors don't change the spinor. Only the theta and phi parameters matter because they determine where the spinor points on the sphere. As an exercise, you can try calculating the theta, phi, and omega parameters for this spinner of length 1 that's been rotated around, and try checking that the flag orientations make sense. So, spinors are pairs of complex numbers where the overall multiplication by a non-zero complex number doesn't change the spinor. This probably seems very mysterious, but there is a way we can understand spinors better, by realizing they are members of the complex projective line. The complex projective line is a bit confusing when you first see it, so let's start simple and look at projections in the ordinary two-dimensional space with real numbers, which is the xy plane. Let's imagine that we have a vertical screen at the position x equals 1, and we want to project points onto this screen. One way to project points is to send them along parallel lines at right angles to the screen. This is called orthogonal projection, and it maps the point xy to the point 1y. The y-coordinate stays the same, but the x-coordinate is forced to be 1 after the projection. With this projection, objects retain their true vertical sizes after the projection. Another type of projection is called perspective projection. For this, we put our eye at the origin point and project all points in the plane towards our eye using radial lines. The locations where these radial lines hit the screen are where the points end up after the projection. With perspective projection, the true size of objects is not retained after the projection. Objects that are farther away from the screen will appear to shrink more than objects that are closer to the screen. With perspective projection, all the points on this diagonal line through the origin will be projected to this same specific point on our screen. We normally write the equation of a line as y equals mx plus b, where m is the slope and b is the y-intercept. However, since our projection lines go through the origin, we have b equals 0. And so the slope m of the line is equal to y over x. This is true for any point on the line, so all points on this line have the same y over x ratio. If we look at the point where this projection line crosses the screen at x equals 1, we find that the y value is the slope m. So all xy points on a given projection line get projected to the point 1m, where m is just the ratio y over x. So the destination point will be completely determined by the ratio y over x. This means that if we scale a point by some overall scale factor a, it will not change its destination point after the projection. All this does is push the point outward along the ray. The scale factor will get cancelled when we take the ratio between y and x, so it doesn't affect the final destination of the point after projection. We call this space after the projection the real projective line, RP1. Now, there are a couple of important details to consider with the real projective line. One thing to consider is this point here on the y-axis. Where does this point get projected to on the screen? Tracing a radial line towards the origin, the resulting ray points downward, parallel to the screen, and goes on forever. So this point doesn't get projected to the screen at all. We say that points like this get projected to the point at infinity. Any point with a 0x value will get projected to this point at infinity, because the y over x ratio involves division by 0. This point at infinity can be reached by projecting downward along the y-axis or upward along the y-axis. So there is a single point at infinity that can be reached by projecting infinitely in either the positive or negative directions. This point at infinity sort of joins up both infinite ends of the screen, so that it forms a continuous loop. This idea of a point at infinity might make you feel uncomfortable, but this is a perfectly valid mathematical object in projective geometry. It's just an extra point we include for projecting points parallel to the screen. Just remember that all xy points with the same y/x ratio get projected to the same point on the real projective line. And in the case of xy points where the x-coordinate is 0, all of these are considered equivalent and are projected to the point at infinity. Although, keep in mind, the origin point does not get projected anywhere, and is ignored for the real projective line. The second thing I want you to consider is the left half of the plane behind our eye that's at the origin. It's important to remember that points behind our eye will also get projected to the screen. So if we look at this circle, these 2 points on opposite sides of the circle will get projected to the same point on the screen, because they exist on the same line on the origin. Any 2 points on opposite sides of a circle centered at the origin will get projected to the same point on the real projective line. The projection can't tell the difference between the positive version of a point and the negative version of a point, because in both cases the y/x ratio is the same. The projection doesn't care about overall scale factors of -1. So if we take a semicircle and project all of its points onto the screen, we'll cover every single point on the screen, including the point at infinity. Watch what happens to the projected point as we travel along this circle. The projected point goes off to infinity and then comes back after a half turn around the circle. The next half turn on the circle corresponds to another loop on the real projective line. So 1 turn around the circle corresponds to 2 full turns around the real projective line. It's almost like the projection takes the circle and makes it curl around on itself, so that it wraps around twice instead of just once. So that's the real projective line. We put a screen at x=1 and project all the points in the plane along radial lines connected to the origin. The destination points are completely determined by the ratio y/x, and so overall scale values don't matter. Points on the vertical axis are projected to the point at infinity, and points on the opposite sides of a circle will end up projected to the same place, because projection destroys the difference between positive and negative versions of points. Now, it's possible to do this in higher dimensions as well. We get the real projective plane, RP2, by projecting all points in 3D space radially from the origin onto a flat 2-dimensional screen at x=1. In this case, the resulting point on the screen only depends on 2 real numbers, the ratio y/x and the ratio z/x. We saw the real projective line is like a circle with opposite points made equivalent. So it's like a semicircle where walking off one end teleports you to the other end. The real projective plane is like a sphere with opposite points made equivalent. So it's like a half sphere where walking off the edge teleports you to the opposite edge. We can use a similar approach for real projective spaces in higher dimensions. But let's get back to spinors and consider the complex projective line. The complex projective line is very similar to the real projective line, except instead of dealing with a pair of real numbers that are unchanged by real number scaling, we deal with a pair of complex numbers that are unchanged by complex number scaling. Unfortunately, it's basically impossible to visualize a space of 2 complex numbers, because this would involve 4 real dimensions. But the mathematical reasoning works the same as the real projective line. We project our alpha-beta points onto a kind of screen located at α=1. The position on the screen is entirely determined by the ratio beta/alpha. Points that have a coordinate of α=0 will get projected to the point at infinity, since this results in a ratio of beta over 0, although we ignore the origin point when doing projections. After the projection, we can no longer tell the difference between the positive version of a point and the negative version of a point, because they both have the exact same beta over alpha ratio. In fact, we can't tell the difference between any two points scaled by an overall amplitude and complex phase, because these also go away when we take the ratio beta over alpha. The flagpole sphere is how we visualize points in the complex projective line, with one of the sphere's poles being the point at infinity. The ratio beta over alpha completely determines the direction of the flagpole on the sphere. We've seen this sphere called the Poincare sphere and the block sphere, but in the context of the complex projective line, we call it the Riemann sphere. If we go back to the 6 main spinors we've been looking at for the last few videos, you'll notice that they are all completely defined by the ratio of their two components. The spinor with alpha equals 0 represents the point at infinity. I'll briefly mention Mobius transformations, which are general matrices that act on a spinor. By treating the inputs and outputs as single complex numbers given by the ratios of the spinor components, we get this function here called a Mobius transformation. I'll talk about this more in future videos. So we now have a good mathematical description of what a spinor is. It's a member of the complex projective line. In other words, it's a pair of complex numbers that have been projected so that the overall scaling and overall phase factor doesn't matter. It's only the ratio of the two components that matter. The result of this projection is that a single rotation in the original space before projection results in 2 full rotations in the space after the projection. Because in the projected space, we can no longer tell the difference between the positive and negative versions of a point. Each point on the complex projective line is determined by 2 real numbers, and so we can draw the points on a sphere, determined by 2 angles, theta and phi. If we want to visualize the overall phase of a spinor, we can view it as the angle of a flag that is spinning around a flagpole. And the overall scaling factor can be visualized as the length of the flagpole. But neither the angle of the flag nor the length of the flagpole change the location of the relevant point on the sphere, and so they don't actually change the spinor. So we've closed the first chapter of our journey into understanding spinors. We have a mathematical description of spinors that works and can be applied to 2 different physical problems. But there's still more to learn. We'll see later that we can write 3D vectors as 2x2 matrices that rotate with double-sided transformations, using a pair of SU2 matrices. If you're familiar with quaternions, this is equivalent to rotating a vector with a pair of unit quaternions. We're going to see that we can factor this 3D vector into a pair of spinors, and each spinor will rotate with a single SU2 matrix. In other words, spinors transform with a single quaternion instead of 2 quaternions. We'll also see how we can find the higher dimensional analogs of the quaternions and SU2 matrices. For example, in the 4-dimensional spacetime of special relativity, we'll generalize the quaternions to the matrix group SL2C, which will allow us to do both rotations and reference frame boosts, giving us 6 types of rotations for spacetime spinors. Also, I've left a few links in the description to other sources that discuss physical applications of spinors and the flagpole visualization.